Good afternoon, everyone. I am Gokul, and joining me today is Sazara. We both work in Amazon S3 tables, and today we'll talk about correctness techniques for Apache Iceberg compaction. And what do we mean by correctness? We don't mean did your compaction job run successfully or not. We're talking correctness at a much deeper level, which is after compaction is done, is your table looking the same before compaction? Does it have the same schema? Is it maintaining all of your snapshots? Does it have the same rows, columns, values? Is it still readable by all the engines that are using that table? So with that, let's dive in. Before I get into sort of the details of the talk, I want to talk about Amazon S3 tables, which is a fully managed Apache Iceberg tables provided by Amazon S3. And obviously, a lot of you are aware of S3. Probably a lot of you are using S3 on a daily basis. And the way to think about it is tables is a managed tables primitive that is being offered by Amazon. It is purpose-built for Iceberg, and it is fully compatible with the Iceberg spec, and it works with the Iceberg REST catalog. Why use S3 tables? Because it's designed for optimized performance, where we do a lot of background optimizations like compaction, orphan deletion, snapshot expiry. We have designed it in a way so that it offers more TPS than if you just run Iceberg on regular S3. The second thing is we provide simplified security by integrating with IAM, telemetry from CloudWatch, and audit logs from CloudTrail. And finally, we do cost optimizations with intelligent tiering that automatically moves the data to its most cost-effective location. More than that, we also offer other features like cross-region, cross-account replication, and so on. But this talk is not about tables. It's about Iceberg and correctness of Iceberg. And the reason we are doing this work is to build and maintain customer trust. Of course, S3 tables supports Iceberg tables. That's a given. And compaction is a core maintenance operation. But everything we talk about here is about the Iceberg spec itself. It doesn't tie itself to a very specific implementation of tables. And the reason we focus on this is because we want to maintain the correctness of compaction, because that directly equates to customer trust. And we want to build on that. So with that, let's start with an Iceberg table. This is a picture that probably all of you or most of you have seen. If you have read the Iceberg spec, you would have seen this picture, or you would have seen copies of this picture in many other websites. So this is an Iceberg table. It has at the topmost level a catalog, has a metadata layer which consists of metadata JSON, manifest list, manifest files, and then finally at the bottommost level you have data files and or delete files. So this is what we think of as the physical layout of a Iceberg table. Logically, when all of this gets materialized and an engine is scanning this table, they see a table with a bunch of rows and columns. So to abstract away some of these details and to focus on compaction, let's represent it in a different way. Ignoring manifest, metadata, and all of those things, what you really have is an Iceberg table that consists of data files and delete files. And over time, depending on your workload, you may create lots of small files because you're doing small ingestions, or you have lots of delete files because you're churning through that data. And what does compaction do? Compaction takes this table, which has many small files, delete files. It applies the deletes to the data files. It coalesces the data files together. And at the end, it creates a table with fewer but larger files. But after compaction, the table still looks the same. It still has the same rows, same columns, same values. So the way to think about it, and this kind of leads you into sort of the details of what we are trying to do, is that compaction does a physical transformation. It changes the files, but at a logical level, it remains the same. So everything must remain the same. And this is sort of the fundamental insight that we're using to build correctness for compaction. And why do we focus on correctness of compaction, right? Like, as I mentioned, correctness directly leads to customer trust. And what are all the things that can go wrong? For example, here, I take the same table. Instead of a data file, I put like a delete file underneath, which happens to be a position delete, removing the entry for Carol, which happens to be the third row in that file. Now, during compaction, a bunch of things can go wrong, right? When I scanned it, I forgot to see the delete file, or I read the delete file, but I interpreted this value incorrectly, and I didn't apply it properly. Or when I did the commit, I wrote the metadata in the wrong way. Any of those errors could effectively lead to this row reappearing, so data being resurrected, and this is a correctness problem. And there are other things that can happen as well. For example, as part of compaction, we can drop a snapshot, and this is going to hurt your time travel queries. Or we add an incorrect link from the manifest list pointing to an old manifest file. Or when you're writing the compacted data file, you could be using incorrect encoding, and then suddenly your table is unreadable, right? So when you look at each and every one of these links and objects and things, what you will see is that there are hundreds of constraints and many things that can go wrong if you have a buggy code. So how do you know that you handled and identified these constraints and you're handling them all? And this is sort of the core of the talk that we're going to get into, which is how do we do the validation, and how do you know that the validation is correct? And this is where I will hand off to Cesara, who's going to talk about that.
Thanks, Gokul. Hi, everyone. At the core of our correctness argument is the specification. And what I'm going to present next is how do we connect the specification with the implementation of compaction. Before I dive into that, let's align what the specification says. So compaction creates a new commit. The files that are created by this commit need to respect the Iceberg specification. So they need to be organized into manifest libs, and snapshots. They need to have timestamps, sequencers, so on and so forth. The second part is specific to compaction. We need to create, compaction creates a new snapshot. Its sequencer is higher than the sequencer of all the previous snapshots. And the content that the query see before and after compaction, it's the same. The logical equality. And what we are doing now is connecting the two, the specification and the implementation. And the main insight here is that we have introduced a new phase. So we start with a table, we run compaction that stages the files that have been created, and right before committing, we have introduced explicitly a validation phase. And this validation phase is the one that is checking the specification. We are running validations on the table before the compaction and the table after compaction. Like this, if you're starting with a broken table, you want to know before compacting it, maybe you decide not to compact. So what are the runtime validations implementing? Going back to the Iceberg specification, to the Iceberg table view. The validations check properties of the metadata JSON file. For example, the snapshot that you have created has the highest sequencer and the highest timestamps among all the other ones. They are talking about a manifest list, about the manifest, so we have validations at every level, including the data one, so we do checks on the number of rows, the number of files, and we have also validations on the content. We are actually checking that the content that the query sees before and after compaction is the same. Now, some of these validations we can efficiently implement because the Iceberg format has already all the metadata that is required, easily accessible, most of the times in the metadata file, like the sequencer, the timestamp, snapshot IDs, so on and so forth. Other ones, there's a very big gap in the Iceberg specification, the fact that there's no checksum on the row content. Therefore, for us to implement the validation of the content preservation, we need to read the snapshot before compaction, like any query engine would do, and compare it with the snapshot after compaction. So if we were to have actually a row content checksum, then we could perform even this validation super efficiently at runtime. Now, this is a very powerful abstraction. If you think of compaction code, it's an extremely complex code. And when we take this view of separating the implementation from the validation, we realize that for now the compaction is a black box. It can be any compaction. All compactions, whether it's Spark or the one that you want to implement tonight using your favorite AI, they will all have to maintain the same spec, and running these validations will hold for any compaction. So that's a very big, so that's actually an extremely powerful enable, because if you're thinking in terms of automated reasoning, if you're thinking in terms of how can you ensure the correctness of your code, going into the correction of the actual implementation is a nightmare. You have dependencies you have to take care of. You have complex code, different language features. Well, in the world of writing validations, it's clean, it's much simpler, it's contained, so we can actually guarantee coverage of the specification in terms of implementation of the validations. So how do we validate the validator? We have actually implemented our own table generator. It generates correct and incorrect tables. The table generator is built in a way that covers the specification, insurance coverage of the specification. So we want to exercise these validations not just on any table, but we want to exercise these validations that they work as expected, even on corner case tables, that when you're doing your most fancy way of updating the commits, there's no special case or that will escape, and the validation will not know how to deal with it. So what does this mean? It means that on the positive, on the correct tables, the validations succeed. And if on a correct table a validation fails, then we need to strengthen our validations. If the validation fails, then it means our implementation, we need to strengthen the code of the implementation, we need to fix the bug, and vice versa. If a validation fails on a correct table, then we need to strengthen the validation. Now, mutation testing to generate positive and negative, correct and incorrect tables. There's a variety of ways of doing mutation testing in the world. We have taken an approach based on rooted in automated reasoning principles. So we are formalizing the specification as first-order formulas, and by negating the formulas, we are generating a mutation for each disjoint in the negation. Let me give you an example. So one of the properties that the compaction has is the new snapshot needs to contain all the files in the snapshot before compaction. They may be marked with deleted or existing, but all of them need to be in the new created snapshot. The negation of this formula says there exists one file which disappeared from the snapshot created by compaction. And then how do we mutate then? We randomly pick a file and we just remove it from the metadata, from the Iceberg DAG. Now, this guarantees that the table that we have mutated is an incorrect table, so validation should catch that. But now if you have a very large table with, I don't know, thousands of data files, do we really increase coverage if we pick yet another data file? Not really. The chance that two of them are going to be similar is quite high. So this is why we decided to go a little bit even deeper and challenge whether really tables have to be big in order to give us good coverage for correctness. And if you think of real-world table, yes, they are very large, but they are also typically obtained on the happy path. They don't really cover corner cases. And let me take some examples. Here is a table. We have lost, after the compaction, a row, Carol 75, was lost. Sorry, Carol. Do we really need a table with, like, this bug manifests itself on a table with 100K rows? Actually, we need just two. We need a table with 2 rows. Carol, the one that's lost, and another one in the same file or in different files. Similarly, if we have a delete, there's a zombie, Carol has been resurrected, the delete was not applied. Well, do we really need 100K rows, a table with 100K rows to spot this bug? No, actually 2 rows and 1 position delete are sufficient to see the bug. So are we being lucky here? Is this just a coincidence? Not really. There's a deep mathematical result. Actually, there are these logics that have what it's called the small model property. And in a nutshell, what this says is you have a formula, and if a formula has a model, then it has also a model of bounded size. A model for a formula is an evaluation for its variables. This, in terms of compaction, means that if we find a way to specify the compaction, that the formalization is in one of these logic with the small model property, then what we get is, okay, there's a bug that manifested itself on a large table, then there exists a smaller table that we can reproduce the same bug in. So here in my picture, bug is the formula, and model is the table, big or small, bounded size. So this is where it gets interesting, and this is where what Gokul said, that this fundamental view of taking the logical content and not the entire physical representation into account, it's a very important insight. So our specification talks about content preserved by compaction. So, you know, the set of rows before and after are the same. Our specification does talk about deletes because we do want to capture things like, oh, there is a zombie entry that was resurrected. But our specification does not talk about the metadata file, the metadata JSON, does not talk about the manifest and the entire tree structure of Iceberg. And when we do that, so actually it turns out that 6 rows are sufficient. It's a very small bound, so then we can actually enumerate all possible tables that you can create with 6 rows, all possible Iceberg table, all possible data representation, disk representation of your table. And to give you a little bit an idea of how powerful this is, so if we want to enumerate all tables with 6 rows, we need to take what? Take those 6 rows and map them into all possible ways that they can be mapped into files, and afterwards these files into snapshots and order the snapshots. In simple terms, you have 6 rows. You can do append row 1, append row 2, append row 6, one way. Or now you have a delete row 1. Then you do append row 1, delete row 1. Append row 2, append row 3, append row 6. But I can also do append row 1, row 2, and then another delete row 1, and then append row 1, row 2, 3, 4, 5. So now this entire combinatorial, this is what our table generator takes into account. And in terms of numbers, we are generating 62,000 tables. And if we were to consider tables with 1,000 rows, just the first step of putting 1,000 rows completely exhaustive into files would lead us to more stars than the universe has. This is the number there, 2 to the power 10 to whatever. So this is the reduction that we have obtained. And basically, if you're thinking in terms of which bugs this one helps us find, it's the planning phase of your compaction. Maybe mislabeled the files that need to go in scope for compaction, forgot some, added some that shouldn't have been added, so on and so forth. This is not the only thing that we do, because there are other bugs. So now we take this 62,000 layouts and we start adding, and now we start adding data to them. So we are populating these tables with different data types, different encodings, different compression types, because we want to capture bugs where the reader and the writer, use different rounding algorithms and corrupt the table for completely, data reasons, content reasons. Other things that we do, we blow up some of the files. If you think of bin packing, right? 6 rows, you want bigger files, right? You have constraints in there. Then we are just gonna pick up some files and just, randomly increase their size. And finally, we are evolving the table, adding new columns, change the partition, because we wanna make sure that, compaction behaves correctly also when the table evolves. So the layout is an exhaustive enumeration of all the possible disk representations of your table, and the other ones are randomized. And with that, oh, I can tell you about some of the findings that we had. So in the beginning, when we did the validations, we focused a lot on the snapshot created by compaction, and we forgot we omitted the fact that, compaction, the commit created by compaction needs to preserve all the history of the table. So, you cannot flip the sequence out of one of the previous snapshots or the timestamp, because then it may be expired too early. We also found that when Iceberg specification is not precise, like when it comes to the key value in the metadata of the Parquet file, then compaction may ignore completely and remove this metadata from the Parquet files. And with that, I think I will conclude my part and hand it back to Gokul.
So yeah, so I think Cesara covered a lot of the technical details, the formal foundations behind what we did. But I think the way we look at it is we are bringing forth a set of ideas, a set of tools, and we want to share it with the community, and we want to build with the community to bring this formalism to Iceberg, right? So the sort of table generator is something that we have built. It's a standalone library that generates these tables, like Cesara mentioned, and we plan to open source it soon. The second thing that we are doing is we are building a more generic spec validator, similar in concept to what we described in this talk, but covering more than just compaction. Maybe we'll cover snapshot expiry, we'll cover orphan deletion, or maybe even just appends and deletes that the commits that happen there. And the idea is that we are taking the Iceberg spec that you see on the website, which is in plain English, when we want to formalize it step by step by converting to YAML, to SMT, and then do the model checking, and then build this validator that anybody can use to plug in and ensure the correctness of the various operations. And the other thing that we want to do is something that Cesara briefly mentioned, which is we can do a lot for Iceberg metadata, but the row checksums is something that is like lacking in Iceberg. And so we want to have a discussion. Maybe we can talk after this presentation about how do we think about that. And we have some ideas, but I'm sure a lot of others have better ideas. So in the end, like what we are trying to do is our goal is to contribute these techniques and tooling to the community. There is nothing secretive. It's all Iceberg spec and correctness of that spec. And we want to get feedback and help to improve that. So with that, just wanted to conclude, right? So correctness is a solvable problem. We don't have to create billions of tables, even with 62,000 tables. We have nice bounded properties that say that we can ensure correctness of compaction. And what we're doing is we're taking the English spec that you see on the website and converting them into invariants that you can plug into your runtime system. And what we find is using the formal foundations of small model property, we can cover and we can focus our testing in a much better way than random testing itself. And finally, what this is sort of a call for action, which is we will open source all the tools that we build, and we want the community to engage with us, add to it, build similar tools so that we all benefit. And that's all I have. Thank you so much.
Let me ask the question. Thank you. How did you found out that the compaction correctness was violated? Was it during like routine testing, or what triggered all of this logic?
So I think a lot of the motivation comes from the fact that we're in S3. So like when you use S3, we focus a lot on like availability, durability, integrity. So in general, in S3, we build tools to like check our code. We do formal verification of our code. So that sort of mindset we're trying to build to Iceberg because we are S3 tables. We want to make sure the compaction that we do, all the background maintenance operations we do are correct. And that's sort of the motivation behind doing all this work.
Hi. So the compaction that happens under the hood in S3 table, if the validation is already baked into it? Yes. Is it? Okay. So if that's the case, like, what is the latency you are inducing it? Because now in modern lakehouses, like the timing is the key. Even though you have one single delete record, compaction kicks in, right? And people are struggling, like, the compaction is doing in the same time read, write, like the conflict. So what are the latencies inducing it? Do you have a benchmark, any data point you can say?
So the question you asked is a very valid question, right? So the metadata validation doesn't take that much. And then the reason is because we are creating all these files. We can put the validation in line to do it. The data validation gets tricky, especially when you have bigger tables. This is where some sort of checksum within the Iceberg spec would be super valuable. But when we don't have that, we have to make trade-offs in the sense that we have to do data checksums for like sampling, right? We have to say, every X commits, I will do this data checksum, or if I'm doing a big compaction, I'll take fragments, like batches of the compaction that I'm doing, I will do data checksums. And that's how we sort of keep it down. So in general, like, there is a hit, because obviously we are doing this validation, but we amortize it by sampling for the places where it's heavy, and for the places where it's not that expensive, we do it for every compaction.
How do you figure it out? Like, if I have 100 million rows in a table versus like 100 records, so if the compaction looks at some table stars which were static, or like there's a different way that
Yeah, I don't know how much I can get into it, but we have a lot of heuristics on when to schedule compaction and so on. Yeah. And we are looking at sort of how the table is evolving to figure out all that. I can talk to you offline, but yeah, there's a lot of intricacies there.
Yeah, just maybe, following up on that subject a little bit more, can you do any sort of like data pruning or partition pruning when you're doing compaction to actually limit the scope of files that you verify instead of having to necessarily do subsampling or something like that? Like, you're only touching a subset of data files, so you don't have to select star everything in the table and only...
I think that's the wrong question to ask, and I'm going to be very bold about it. Go for it. What's wrong with adding checksums? Why do we have to do a dance around it and find like 100,000th way of, going around a problem instead of going straight to the problem, face it and solve it? What is the main, you are the community, right? What is the main reason we do not have checksums, content checksums in Iceberg? Is there a fundamental thing that, prohibits us in having it?
I don't know that I have a checksum, but do you see encounter an issue with the correctness if I just do Spark, rewrite data files? Like Spark provide that, like compaction, right? If I do that, like, out of 100 tables I have, do you think like there's a 10% chances I run into data incorrectness or data issues?
I mean, 100% chances. In S3, we don't take that approach. One bit flip, and they do happen when you are running like, I don't know, terabytes of data, they happen at every hour, bit flips. Each bit flip is going to change the table. If that bit flip happens during compaction, your table is going to be wrong at the end. Whether you care or not that, some of your entries are wrong, this is a different, right? This is like you're managing your Iceberg table and you know what you want. But in S3, we do not want not even one record to get corrupted. We want to have it right, and we want to do everything that's possible to get it right.
To what extent can you leverage S3 existing checksums there?
We need a row content checksum. There's nothing that we can do. Like, we can, again, dance around and get a little bit better. We do have S3 checksums, so everything comes with a checksum from S3. But if we are really talking about a table content, there's just going to be patches, not real, solutions.
Yeah, so agree on like checksum being like a possible thing to do for like data consistency at the runtime. But I wanted to understand a bit more broadly, like you like designed all that validator and testing for the validator, were there any other runtime invariants apart from checksum that are more interesting, or is checksum the only invariant? Because one part is definitely like spec validation, but which is different in my opinion from like runtime validations. So what were the other interesting runtime validations that you were able to find?
So we are, do you want to take this one? So our validations cover everything. We don't want to omit anything in the validation. We want to have in the validation every single thing in the Iceberg spec. Every single time there's, required field in, there is a validation that says your commit has that required field present. Every single time the spec says, the spec does say that the snapshots can be ordered, and the order of the sequencer and the order of the timestamp, it is the same. We want to have that validation. The spec says the last commit, the last sequencer equals the highest sequencer in the table, of the snapshot in the table. We want to have that validation. So we really took everything, every single thing in the Iceberg spec and encoded it into this validator. Now at runtime, there are everything that has to do with Iceberg metadata, we can run efficiently at runtime. We did not incur penalties, performance penalties, except for the row content, the equality of the row content, where because of the lack of checksums, if we were to have checksums, it would not be a problem. We could run it at runtime on large tables. There won't be an issue. Everything else besides that, we have it.
A couple of questions, just to clarify, because I might have missed this in the beginning. So you wrote this validation. So a few questions. You wrote this validation. Are you using the Spark rewrite data files, or do you have your own implementation? What is this testing? Is it testing what's is a presumption that you have your own implementation, you wanted to test the correctness of your implementation, or is that there's no validation whatsoever in the Spark job right now and everyone is corrupting their files every once in a while? And what is the scope of this validation? And two, is the plan to build this back into Spark rewrite files job that everyone is using? Because presumably you're running this in production at runtime to validate all this. Is this something that will be AWS specific because you have your own implementation, or is it something that's in the future going to be a part of it? And then since you're running this at runtime, do you actually see corruption at large scale across, is basically because of lack of validation, does everyone's files get corrupted every once in a while? Is this something that's happening, or I don't know?
So what you ask are very interesting questions, right? So I think when we designed the validator, we didn't want to tie it to any particular way of compacting. We didn't want it to be Spark specific or something that we want to build in-house or whatever, or maybe somebody else has a better one, right? The way we are looking at it is there is a black box compactor. It is going to create a new snapshot, which happens to be the table that would be committed, if it went through, right? So we call that the staged commit. So at that point, you can hook into our validator. And what we're saying is there is a pre-image that we started out from. We are doing the compaction operation, and here is sort of the staged post-commit table. That's all we need to go and validate everything. So we are validating based off of that. So to answer your question, once we have it, can we plug it into Spark? Yes. As long as we don't finalize the commit, you can give us sort of the staged one, and then we can validate, and then you can let the commit go through. And this should apply for any such compactor where you can give me a staged output.
My question was more a lot of people are running Spark Compaction. So is the idea that we build this inside of the Spark Compactor and everyone starts using it, or is there trade-offs that everyone will have to?
No. I think the final shape is we can decide as a community, right? The validator right now is completely independent. We are planning to open source it. If that code gets pulled into the Spark code base and we call that same thing, it's fine. Like we're not holding back on that.
Well, my presumption is that you're saying you S3 as a business unit, like they have certain policies for correctness. So is that was driven by that? Meaning like you need to run this in production, therefore you will do it, and then maybe the industry will catch up with it. Is that an idea or?
Yeah, I think the thing is we want to do it because we are S3, right? And the thing is, we don't want to hold on to it. Like this is a nice thing to have for the community. So if tomorrow we want to integrate it into Spark, we will integrate it into Spark. There's nothing holding us back.
Yeah, so I have two quick questions, and the first one is like, how do you choose the compaction size? And second one is, how do you handle the commit conflict?
So both of these are good questions. So the compaction size. Okay, I think we are over time maybe. Yeah, but anyway, this will be the last one. So compaction size is actually an option in the S3 Tables API. So customers tell them what is their sort of target file size. So we are not deciding on that. What was your second question? Commit conflicts, correct. So commit conflicts, again, it gets tricky. But what we are saying is compaction is doing this, and then obviously when there's a conflict, there's a rebase. So you have to account for that. Yeah, we didn't go over it, but we can talk to you offline on something like how to do that. I think I'm just going to say we'll talk offline because we're running out of time.